Hi, I'm Tom Sulzer, co-founder of Sulzer Schmid. I'll be talking about taking rollerblades operation and maintenance to the next level in the age of digitalization. And we'll see in a minute why artificial intelligence is playing a very important role in that. So now worldwide, there's more than 1 million of these rollerblades in operation. And they have one thing in common, they all need to be inspected. And this is an enormous challenge. So why do we inspect rollerblades? It's all about cost reduction. It's all about producing energy at less cost. Now, what does this mean in specifically? We inspect to avoid blade failure because replacing blades is a very costly proposition. If we detect damages early, then this is an opportunity to repair them at a lower cost than letting the damage grow over time. We also can identify at times manufacturing defects, which helps the OEMs to put together a mitigation plan. The repair scheduling is an important component in when we talk about cost reduction, because not every damage has to be repaired right away. And if we have very detailed information about damages and also how they develop over time, we can optimize the repair campaigns. The validation of the quality of repairs is another angle, which is important. Then also, oftentimes, wind parks change hands. They're sold to a new owner, and this new owner wants to have a great deal of transparency regarding the condition of the assets, so we can support that with blade inspections. Sometimes there are discussions with the insurance companies, and that's yet another use case for rollerblade inspection. And in certain countries, there's legislation in place that mandates such inspections. But the biggest one of all is probably moving towards predictive rollerblade maintenance, because that could yet again unlock great cost savings potentials. And prerequisite to that is that we collect trustworthy and structured inspection data over several years to from that develop an understanding of how damages behave and how they develop over time. So for all that, we put together what we call our 3DX blade platform. And what you see at the top right is where things start. We are capturing data, we're documenting the entire surface of the rotor blade by means of autonomous drones. And what was important there is, of course, that we can achieve efficient field operations by minimizing training requirements. The drones have to be ruggedized to withhold or withstand harsh environments and so forth. But so it starts with data capture, and these drones, they accumulate a great deal of data in short time, and all this data needs to be processed. This is the playground for AI, because the processing by humans is very time consuming. AI can do a great job in reducing the time that blade experts had to invest previously. Now, the purpose of AI is to find anomalies. And anomalies are exactly those regions or areas that the blade expert should have a closer look at, because the blade expert will ultimately be responsible to assign detailed classification information and severity to those anomalies, turning them into damage findings. Now, you can imagine all this information is captured in a database, and now we can run powerful analytics across these data sets, which will really give us a much deeper insight of how these rollerblades behave, how they behave in different environmental conditions, for example. And from that knowledge gained from the data, we can also deduce the appropriate actions to be taken and optimize the intervention programs. So we kind of look at this as a whole ecosystem by now. This is just to give you an example how the data is captured. You see here an autonomous drone flying in close proximity to the blade. There was a lot of development involved only in this part. We are navigating with LiDAR, with laser sensors, to assure the repeatability of the process and also to support the determining of the location and size of the damages. So the entire data capture process is completely repeatable. The drone can be looked at as like an NC machine tool. And of course, the image quality is of absolute importance here. This is just another chart to give you an idea of what the kind of data volumes we're talking about. Typically for one turbine, we're collecting something in the neighborhood of 5 gigabytes. And if we extrapolate that to a year's worth of inspecting, you can see, and this year we'll do probably 10,000 turbines, which will be close to 50 terabytes in imagery data. So it's an enormous amount of data that we have to process. And we kind of broke down this process into several steps. Again, on the left side, you see the data capture, the inflow of raw data. And this raw data images, they are pushed through the AI engine, which is a trained neural network. Nnaisense, our partner in this for the AI part, will talk more about it in a minute. And again, as I said earlier, the purpose of AI is to find anomalies. And those anomalies are served to the blade expert for detailed examination. For that part, we've developed a piece of software, we call it Blade Station, which supports the work of the blade experts and makes that process very efficient. So from images, and it's important to say that the raw data has to be of high quality and should be captured in a repeatable fashion. We're processing all the way to the right side where we have detailed damage information. This is what you can see here. Raw data through the process turns into structured data, which is captured in a database. For each damage, we have detailed localization, size information, classification, severity, and additional metadata. Now, from that data, again, we're getting into the analysis section now. You can easily imagine that we can consolidate this data. First, we look at all the damages on a turbine. We can visualize that. We can statistically analyze that. We can then further consolidate from the turbine to the wind farm, where we might have 100 turbines in a farm or 50, or even further up to an entire fleet spanning across many countries. And these are the tools that we use for that. We can also use these tools to look at damage progression. So what happened to this crack that we've seen last year? What happened? How does it look this year or the year after? Does it grow or does it not grow, for example? All this is part of the scope of the 3DX platform. Now, more specifically, here is an example where we have some analyzed statistics, maybe across a park or so, and we see in this case that erosion and coat damages are the predominant issues, followed by several types of cracks. And on the right side, we see the breakdown in severity. Now, severity 1 damages, they're more or less cosmetic damages, whereas a severity 5 damage will basically cause the operator or owner to immediately stop the turbine because it's at risk for a major failure. And the distribution of these different severity classes is very uneven. Of course, we have a large number of cosmetic damages, and fortunately only a comparatively small number of severity 5 damages. And what we can also say is that, over the lifetime, over the 20-year lifespan of a turbine, there is probably not one blade that has not needed any repair. So blades, they age, they're exposed to these harsh environments. Another interesting example shown here is where we look at two turbine types over 2 different years. And this kind of shows that different types or different makes of blades, they might age or they might, respond to different environments differently. So in this case, the blade B shows much faster degradation in the same environmental conditions than blade A. Now back to the quality aspect of the data, in our case of the imagery data. We kind of say now that we look at it as an investment into fleet performance or an investment into the future. Now, traditionally, inspections have been carried out in a given year. The results have been analyzed. It was determined that this and that need to be repaired. And after that, the inspection data was pretty much shelved or discarded. But nowadays, as we are, turning inspections, or as we are gathering structured inspection data, we'll be using this data again in the context of damage progression and predictive maintenance. So it's really worth to focus on high quality data capture as the foundation for all this. And it's not, of course, it's not only predictive maintenance, but also what we understand now is that certain types of damages, they actually reduce the energy output of the turbine. A good example is erosion at the leading edge. And if you imagine that the tip speed of these turbines can be 300-400 kilometers an hour, 24 hours a day, day after day, and they're operating sometimes in very harsh environments, there will be erosion. And if erosion progresses to a certain point, it has a measurable impact on the output of the turbine. So if we determine an optimal repair point, we can, justify this investment into the repair by bringing the turbine back up to its full output. This is all part of, our mission to make a contribution towards reducing the cost for renewable energy. I'm closing with that, and I'm now passing over to Nnaisense. They will take a much deeper dive into all the aspects of artificial intelligence related to rollerblade inspection. Thank you.
Hi everyone, my name is Asha, and I'm a computer vision researcher at Nnaisense. I'll be going into more detail on the AI engine to power Sulzer Schmid's inspection platform, as presented by Tom. So, why should we even use AI here? Some of the reasons overlap with the advantages of using a computer in general, such as being able to run things at any time of day at high speeds without tiring. In addition, for this specific use case, an AI doesn't require the extensive training and examination required to certify someone as a blade expert. AI can self-improve over time, learning from new data and/or its previous mistakes. Using it, we can reduce the amount of work blade experts need to do overall per turbine, and subsequently the cost. This allows scaling to more wind farms and customers. Now, what is the exact task we're trying to achieve? We want to find the function that goes from an image to an annotation, in this case, bounding boxes. Human blade annotators have learned this function over months and years of experience, and we aim to distill that collective knowledge into an automated model. This is called supervised learning, using existing labels to teach a model how to get from image to annotation. And in our case, we use neural networks as our family of models to train. Our task is most related to the existing field of object detection, where the goal is to place labels, usually bounding boxes, to encompass objects of interest in an image. This typically involves a very large amount of data to be collected, covering not only all the types of the objects to be seen, but also several viewing angles, lighting conditions, occlusions, etc. And acquiring this data can be tedious, but much less so if we have control over the environment in which we actually operate. In our case, the inspection drone flies in a predetermined flight path at a near constant distance and angles to the blade. Thus, the damages that we're looking for will reoccur at similar scales and angles. This means a model will require much less training data than if this were not the case. We've obtained models with respectable accuracies from only a few hundred turbines in total. That's not to say that it's a walk in the park, just throw images with bounding boxes to the model and obtain the results. As with almost any real world application, we have to deal with non-ideal factors such as variance in annotations among the different inspectors, missing annotations altogether, as for example seen in the photo on the right. The fact that defects seen in multiple viewpoints are only marked in one of them at most. And the image size, in our case being 4,000 by 5,000 pixels. In most cases, for neural network-based image tasks, they operate on the scale of only hundreds of pixels in width or height due to computational constraints. So this is much greater than that. Though actually our biggest challenge is the distribution of defect types among all the data. First of all, only less than 10% of all the images actually contain a defect at all. The defects themselves are split into 5 categories, signifying the severity of the damage, as seen at the bottom of the screen. Types 3, 4, and 5 are the main focus of our operation. And yet they comprise altogether less than 10% of the defect categories in total. So we have less than 10% of less than 10%, which implies less than 1% of images contain defects that we actually care about. So our approach involves our detection engine based on convolutional neural networks, outfitted with a custom loss function and scaling of detection layers. We augment the data and sample it in a specific regime to amplify generalization and to deal with a lot of the aforementioned challenges. And additionally, we post-process the predictions using metadata about the image to refine and merge bounding boxes for improved blade expert productivity in the end. Shown here are some sample images of AI-produced boxes capturing defects on turbines. We achieve exceptional accuracies on damage severities 3, 4, and 5, and require less than 6 hours to train on 2 terabytes of data. And during inference time, using an 8 GPU cluster, we can theoretically process all the images from a single turbine in around 1 minute. On top of this, we perform benchmarks using AI annotations reviewed by a blade expert and measured between 50 and 75% reduction in the total time it took to finalize the inspections overall. And shown here are some additional images containing relatively difficult to spot cracks, which are considered critical defects in the field. And our AI manages to catch these. As for some specific numbers, we use validation. We use for validation a golden evaluation set, we call it, containing 369 higher severity damages. Currently, we manage 343 true positives for a detection rate of 93%. We currently get 181 false positives, which at first seems quite significant, but it's worth noting that they often indicate some plausible irregularity as visible in the images to the right. So for example, there are spots in which it's often worth noting that there is something interesting here. The false positives are often one of the two following cases. Either a lower severity defect is unlabeled when it's right next to a higher severity one, but the AI doesn't have this notion of relative importance there and just marks both regardless. Or the second case is where a defect is visible in multiple images, yet human annotators will only label it once, but the AI will annotate it in every instance that it sees. So for this reason, we say that not all false positives are truly false. We can also vary the threshold used to filter out the predictions, and naturally that will decrease both the number of false and true positives. The plot on the right shows this, and as you can see, approximately at least until approximately 0.5, the false positives decrease at a faster rate than the accuracy does, which is a good thing. Additionally, predictions can also become unhelpful rather than helpful when there is just too many. We use a combination of data-driven learned and handcrafted rules to delete and or merge bounding boxes that were predicted by the network to minimize the clutter and the false positives. So in the end, once the training is complete, we package the solution all wrapped up in a self-contained Docker image. This can be used out of the box by almost any cloud provider. And in this case, we deploy it onto Sulzer Schmid's existing Azure infrastructure. The AI engine is triggered by an external HTTP request pointing to the cloud storage where the images reside. And then the engine processes these images and writes the results back to the storage. As a side experiment, we also attempted testing the trained model on blade images taken not from a drone, but from the ground. And despite the differences in angle and resolution, performance was largely comparable, indicating that slight changes in the task environment likely only require a small amount of fine-tuning to reach the previous levels of accuracy once again. And in addition, we claim that the general detection engine that we have is readily applicable to other detection tasks altogether. So now what's remaining? We still need to integrate a feedback mechanism or a human in the loop, as it's called. This will allow inspectors reviewing the AI results to redirect the mistakes back into the training loop, and then we redeploy with an improved model automatically. Furthermore, we also aim to reduce the number of category 1 and 2 false positives even more, and implement a more advanced region of interest merging technique using graph convolution networks. So Thank you for your time and attention. I do appreciate it.
Yeah, hello, good morning, Tom. Good morning, Asha. How are you all?
Good morning. Thanks for having me.
Thank you for being here. Hi, Asha. Hi.
Hello.
Hello. So Tom, you being the guest here, let's get started with some questions for you. I visited your company a few months ago. Was highly impressed. So sort of a Silicon Valley type of high-tech company in the middle of Oberland Zürich, so in Switzerland. not to be found too often. That was my experience. Sulzer Schmid. So Sulzer is you. Schmid is your colleague. I think he's also a Swiss. Is it correct that having your background, you have been in Silicon Valley as well as you told me, plus Tom's background is maybe ideal for such type company, or is this very exotic? And what is the reason that such a company exists? Maybe you can give us a little bit background on the history. Not too long, but I think it's worth it since it's quite special.
Well, I think I'll start with your last question first. I think the reason that we exist, I think, is our entrepreneurial spirit, after all. And the touch of high-tech culture that you might have seen when you visited is probably also explained by the fact that, I spent 7 years in Silicon Valley with a previous company, was also a startup in the digital media field. And so maybe some of that, spilled over to the Zurich region. And Zurich in general has a very, very lively startup culture now.
Okay, yeah. Asha, going to you, actually Silicon Valley, it's a good connection because you are from Silicon Valley, but live now in Lugano, working for Nnaisense. Being responsible for this project, what were your main challenges? I mean, you described a few of them, but maybe again in a few words. Jürgen at his keynote was saying that anomaly detection is at the beginning of our maturity level, but that doesn't necessarily mean it's easy to do. Maybe you can give us a little more insights in the complexity of this project that you were working on.
So, I mean, in general, if you're trying to do general anomaly detection, you would be just trying to find anything that differs from the norm. And that, in general, is a very difficult task, still unsolved overall, especially when you have an uncontrolled image acquisition process. It's not, very, like each image is not taken at the exact same spot, like on a conveyor belt. But so in this case, we're doing, it's kind of a mix between anomaly detection and object detection, like they use with the self-driving cars. And kind of because in that case you can pretty much gather data of everything that you will see, every car, stop sign, truck, whatnot. And in our case, there's a lot of these types of damages. Like a lot of them are unseen yet, and you don't know what's going to happen. There could be many things considered a damage that haven't happened yet. And so, it's kind of this middle ground that we have to stay in, and that's a big research challenge.
Right. So back to you, Tom. Also getting more technical now. When did you realize that you need AI for your business model? Need to automate things, and what is the motivation for you to do so? I think it's quite a competitive landscape now. Is that one of the reasons?
Well, you have to imagine this was like 7 years ago when we started with the project that really led up to Sulzer Schmid, and our first challenge was to develop an autonomously flying drone, because we were believers in in a high degree of automation, and especially in a repeatable process, in an industrial process. So that's where we started, is the development of the autonomous navigation, which by itself is a great challenge. And then, of course, we quickly realized that these drones, they're, accumulating enormous amounts of data in very short time, and all this data has to be somehow analyzed. And I think already back then, at least a dream emerged of an AI solution that would, do all that work. And then it took us probably another year or two to really engage. And luckily enough, we found you to start working on this. And I think we gladly can be proud on a solution that is actually, showing productive results.
Right. Back to you, Asha. So you mentioned the data size, 4K by 5K, is quite big, unusually big. Was this one of the reasons for the complexity and the things you had to do? Also, the quality of the label data was obviously not ideal. How did you overcome these two things?
I mean, the first one we had to, it's in general causes a lot of compromises we have to make, because you can't, process the entire image all at the same time. And you have, because of memory issues. And so we have to find ways to process parts of the image locally, and then reintegrate global information about the spatial, the spatial information of the image afterwards to, to circumvent this. And the second question about the label balance, it's still not 100% solved, right? I don't think that can ever be, but you can just alleviate it to a sufficient degree, and that's what we're doing. We're bringing it down to a point where that's the model can not necessarily have to rely on every single label, and still achieve the accuracy that we need for production.
Right. Tom, ultimately, you mentioned already the workflow or the interaction between now the AI and the human expert is important here. How has this over time evolved? From early stages to now with AI coming into the picture, did you have to also adjust the workflow a bit because of that, or you just is like an augmentation to it? What's coming there?
Yeah, this is an interesting process, because of course at the beginning we had to rely on blade experts, on human beings going through basically every single image. And we developed a piece of software. I mentioned this in the presentation. We call it the Blade Station, and it's a very powerful way of very quickly looking through the images. But still, I think Asha pointed it out. 1% of all the images are really the ones that are of most interest to us, and to kind of weed this out by means of AI is very important. So when we started out, each inspection would take probably 2 hours worth of manual time by a trained blade technician. And now with AI kind of doing this triage, we're bringing this down to maybe 20 minutes, and we'll probably bring it down even further over time. So this is a substantial improvement. It also has a lot to do with scalability. You can imagine how this year we'll do something around 10,000 inspections. Just to find the blade technicians to go through all these images will be very, very difficult.
Right. Yeah, understood. Asha, we have some questions coming in here. I picked one of them. These are technical, so it's your turf. I'm just reading it. How would such a handcrafted rule for determining bounding boxes look like? How did you combine it with data-driven approaches?
Okay, I mean, without going into too much detail about our specific approach, you can train models to post-process the main model's own predictions, and that's kind of our data-driven step. And then you have handcrafted rules that you can put that are based on prior knowledge, from actual blade experts, and also more or less common sense about how labeling these boxes would be most convenient for someone who looks at them or reviews them. And then so you can get merging, filtering, and whatnot from this and you can do both after one another, so that then we have both methods, not in a single step, of course.
Yeah. Tom, back to you. In your presentation, you mentioned two data touch points, I would say. One was ultimately what we are doing, detecting these faults, faults. And then you had a second step as well that you called the analytics, I think. What is that again? And are you using there, or plan to use also some form of AI in the future, or is this not planned and maybe not needed?
I think the holy grail in this whole industry is predictive maintenance. And predictive maintenance is like giving you a crystal ball to take a look into the future, how the condition of these rotor blades will basically develop if you don't do anything. And in order to really get there, we need very solid, structured historical inspection data to understand the dynamics of these damages and also the environmental impact over time. And I think once we get to that point, and we're getting very close now, I think AI will start to play a role exactly in that field too, where we kind of extract the knowledge from human beings and kind of capture that with trained neural networks to actually leverage this data and to make trustworthy predictions about, for example, the optimal point when to repair something or to optimize an entire repair campaign.
Back to you, Asha. Another question here coming in with regards to the false positives. What is the performance, false positives of the detection model on a newly installed turbine, assuming no damage on the turbine?
I should test this, but I mean, in general, when I've tested it on images that were, more or less clean, as I call them, you tend not to get very many, if any, on these, right? There are sometimes, the only times you get some of these on a completely clean image is if there are some markings like text and stickers that are on these turbines, which are not that common. But in general, there usually aren't any in this case. There are a lot more when the turbine is cosmetically dirty. And, there's just a lot of dirt everywhere, and sometimes that can produce a few of these. And in the for blade inspection, dirt and whatnot is not that important, and then these would be considered false positives in some cases.
Just to expand on this, in your presentation, you mentioned that the false positive rate was still relatively high, but didn't totally matter then at the end. Can you expand on this again and explain it again, please? Okay,
so the priority here is not the is the true positive rate, right? We want to get we would rather not miss defects than have too many. So this is the side of this AUC curve that we're aiming for, or just as a priority. And we want to maintain a minimum accuracy level. And then the false positives from there, we just lower from there as much as we can. But the detection rate is of utmost importance, first of all. And then a lot of these, as a false positives, it's just a general term encompassing what are actually true false positives and detections that are plausible concerns, but ended up not being a true defect in a certain category or of relative importance compared to stuff on the blade.
Okay. Tom, we touched on the workflow and how this evolved over time. Would it be even feasible to go yet one step further towards a total automated system that, or is this not something on your roadmap and planned at all? How do you see that?
Well, for the time being, we have the human in the loop, and I think for several reasons. One is that we currently really detect anomalies and don't really chase detailed classification information with AI at the moment. I can see that this might change over time. I think the human will still stay in the loop because ultimately it's also a question of responsibility. Who is taking the responsibility for delivering the inspection results? And I think we're probably better served to keep the blade expert doing this for quite some time. But I can see that we'll keep pushing the envelope in the sense of making the system more efficient and just reducing the burden of the blade experts even further.
Right. So, and for you, it's necessary to push the envelope because of competitive reasons. You being entrepreneurial company and doing new stuff, but of course there are big industrial automation companies out there, and it's 1 million of these wind turbines. You have 1% of it with 10,000, so there is it's quite a big market. How is this necessary for you to stay ahead of the competition?
Well, first let me put this into perspective because some people might think a million rotor blade, this is a multi-billion-dollar business. It's actually not the case because we're facing a lot of price sensitivity in this business. So operators and park owners, they want to pay as little as necessary to carry out inspections and the whole shebang that comes with it. So the opportunity is not big enough to really lure in big companies who would say, oh, we have to go and chase this market. I think this is a very good playground for startups like us to kind of battle this out. And many of us are now active in many countries. In our case, I think we're now inspecting in 35 countries already. So this is the perfect playground for startups to deliver services to an industry.
Okay. Asha, back to you. There's another question. I published this. You should see it. Maybe we have already touched on that. Not totally sure. Hello, what is the performance?
I know it's the other one. It's the one above it, I believe.
The one above. Yeah, sorry. Yeah. Could you please elaborate a bit more on where object detection and anomaly detection approaches combined for this project?
Okay, so this would be going more into the proprietary details of the project. These are more or less covered in the pre and post processing of our pipeline. But also there is a lot of, the project is still, being improved as I speak. And so a lot of these techniques are also still in the research phase and not necessarily in the current version that we are gonna deploy into production. So this is an ongoing live project that keeps improving, and so a lot of these aspects are still not finalized, so I can't speak about them.
All right, good. Tom, final remarks from you. You have to then already stop.
Well, first I want to say, working with Nnaisense, this is a very fruitful collaboration, where we open up this market, and I think the going together with Nnaisense has accelerated our program, and so we think very highly of it, and I think there will be many more things to come down the road coming out of this collaboration.
All right, great. Asha, maybe you want to close a bit on something that we have asked you to do also recently, to look at one of the cloud service providers offering in AI, and you try to basically what they do in their cloud offerings, what we are doing here. How did this turn out? I think you were involved in that, right?
Oh yeah, so I know about this. This was we gave the same data that we have to Amazon's recognition framework, which is their newly released anomaly detection framework. It didn't turn out very well, detection rates of around 10-11% in the end, but this wasn't that unexpected, given that type of platform is meant for very highly controlled image environments, like I said before, on a conveyor belt or something at a factory, where every image almost looks exactly the same. So this, completely automated solutions, I think, aren't ready for tasks like this, and you really need some specialization, some customization, and for this type of data and environment specifically.
Right. So, like Tom, you can also not fully automate the experts. That's good to know. All right. Thanks again, Tom. Thanks, Asha. You have a great day. And
my pleasure.
It was great to have you here. Thank you. Cheers.
Thank
Bye.
you.
Thanks. Bye-bye.
Bye.